This is the context of this screencast. There are two kinds of electrochemical cells. The voltaic cells, which are spontaneous, which produce electricity from chemical energy, and electrolytic cells, which require electricity to do chemical work. Electrolysis is an example of an electrolytic cell. There are three kinds of electrolysis. The electrolysis of pure water, 100% water, 0% salt. The electrolysis of pure salt, which won't happen unless it's molten, that is to say, so hot it's liquid form. That would be 100% salt, 0% water. And the electrolysis of a concentrated salt solution, what we might call brine, B-R-I-N-E, concentrated salt solution. This screencast is an example of the electrolysis of brine solution, somewhere between 0% water and 100% water, somewhere between 100% salt, 0% salt. Now, anytime you have a concentrated salt solution and you're going to pass electricity through it, it's possible that not only your metals or your whatever's happening at your electrodes might experience redox, but water itself could experience redox. When you have a concentrated salt solution, as you can see here, there are two possible oxidation reactions because you have both salt and water that you're passing electricity through. Now, the two possible oxidation reactions, which would happen at the anode, remember oxidation is the loss of electrons. The two possible oxidation reactions would be the one for iodine and the one for oxygen, producing water. These values come from the chart. Obviously, iodine ions would more likely come together to form iodine, and here you have water being produced in an acidic environment because of the hydrogen ions. So these two half reactions are spontaneous as written and are positive. The two possible reduction reactions would be the breaking down of the water or the potassium ions becoming pure potassium. Now you expect these to be negative. You don't expect water to spontaneously, that would mean a positive voltage, decompose, and you don't expect positive ions to spontaneously gain an electron because potassium would like to lose an electron from its outer shell. So both of these values have negative voltages. So the question is which oxidation reaction will occur at the anode and which reduction reaction will occur at the cathode. Now remember that we are providing the electricity to make a non-spontaneous reaction happen. That means that as you increase the voltage of your power supply, the very first reaction that is possible will occur, the one that requires the least amount of voltage, the one that has the lowest hurdle to jump over. And that would be a reaction that has the least difference between the two reduction potentials. And that least difference would be this one and this one. Here's another way to look at it. Imagine, like we did before, that these were altitudes instead of voltages. Imagine that we were talking about potential energy gravitationally and not potential energy per charge, which is voltage. And so we had one altitude at 1.229 kilometers, one altitude at a little more than half a kilometer, and below sea level we had an altitude of 0.82 kilometers below sea level, and this one was almost 3 kilometers below sea level. Which combination would give us the smallest change in altitude? And obviously, if you're going from a positive 0.535 down to a negative 0.8277, that's the smallest jump. That's the least amount of energy you have to provide for the reaction to take place. Remember, we're providing the electricity to make a non-spontaneous reaction happen. Incidentally, you could use an electrochemical voltaic cell to make this electrolytic cell operate. So once we've selected our two half reactions, we write the iodine reaction as a losing electrons as oxidation. Oxidation takes place at the anode. We leave the other reaction as written. And so reduction takes place at the cathode, the gaining of electrons as opposed to the losing of electrons. And so the smallest difference of the possibilities we just talked about, the smallest amount of electrical energy we have to provide, the easiest reaction to make happen would only require 1.363 volts. That's how much energy we would need to provide with our power. Now, in this particular reaction, if we were to actually do it and pass electricity through a concentrated solution of potassium iodide, you could see that we would be making hydroxide ions. And the hydroxide ions could be detected with phenolphthalein and would turn pink at the electrode where the hydroxide ions are being produced. And so what you need to happen then is you would have to hook up the negative post of your power supply to a platinum or inert electrode, which we'll call the cathode. And because it's hooked up to the negative post of the battery, if we make this our battery, and let's say here's the positive post, let's make it look a little more like a battery. So here's the positive and here's the negative. We would hook this electrode up to the negative and this electrode up to the positive. So the negative charge would travel this way. It would be gained. Hydroxide ions would be produced, causing a pink color to form at the electrode that was our cathode. Another thing that would happen at the cathode is you would get all kinds of bubbles forming. Bubbles would form at this electrode as well of hydrogen gas. Meanwhile, at the anode, where electrons are leaving to go back to the battery, as electrons leave, the iodide ions turn into iodine, and iodine is brown in solution. So this electrode, you would see a brown color forming in the water, and at the cathode, you would see a pink color due to the phenolphthalein indicator showing the presence of hydroxides. And you would also be seeing hydrogen gas form.